Hello, everyone. Thanks for coming. I'm Mingyuan, and I'm going to talk about multi-party distributed point function. This is joint work with Arushi and Zhihen. So the primitive we are interested in this work is function secret sharing. In functions introduced by Boyle et al., in function secret sharing, there is a trusted party who, given a function f, generates shares f1, f2, and fn. And each party holding their respective function share and given a public input x can generate a share yi. For the correctness of function secret sharing, we require that the summation of all these shares yi should equals to the function evaluated at input x. And for the privacy, we wanted that if a subset of these parties are corrupted, they should not learn anything about the function f. And in particular, for this talk, we'll always assume all but one corruption. A naive way of realizing function secret sharing is just to take the truth table of the function and then additive share it. That would mean that the efficiency of the share is order of the domain size. So just to get a non-trivial primitive, we require that the efficiency of these function shares needs to be sublinear in the domain size. So DPF, or distributed point function, is basically a function secret sharing for the limited class of function that is the point functions, which are functions that is almost zero everywhere except at one location, which is a non-zero. Okay, so you might be wondering why are we interested in a function secret sharing for this seemingly very simple family of functions? It turns out that DPF is actually very, very useful for many applications of secure multi-party application. It was introduced for related to problem of privacy information retrieval, but later on found many applications where DPF is an essential building block. Okay, so hopefully you're convinced that DPF is a very, very useful primitive and we should care a lot about it. So what do we know about how to construct this kind of DPFs? First, in the two-party case, things looks relatively good. First, in the initial work by Gilboa et al., they show that one-way function is actually efficient to construct a distributed point function. And thanks to the follow-up optimizations, now the two-party constructions are actually even concretely very efficient. And not only that, we also have many follow-up works that construct function secret sharing for families beyond point function in the two-party case, and even optimize the distributed setup phase. However, if you go to beyond two-party, even just three-party case, then immediately we already don't know the share size already square root in the domain size. And as the number of party increases, actually the share size grows exponentially in the number of parties. So this is the only construction, Boyle, Gilboa, Ishai 15 is the only construction we know how to build multi-party distributed point function in the minicrypt. If you're willing to relax the setting a little bit and go beyond the minicrypt, actually, notably, we have a construction from LWE that has polylog key size, but that goes through the FHE machinery. And anything beyond that, we don't have anything that from any other assumptions that has efficiency lower than square root of D. And I want to highlight that this lack of progress in multi-party distributed point function is also has imposed limitations on all the applications that the distributed point function implies. And this kind of limitation is both feasibility-wise and efficiency-wise. Okay, so in this work, we asked, can we find better constructions of multi-party distributed point function in a minicrypt that has asymptotically better efficiency than BGI-15? In particular, we want to optimize this dependence on the number of parties from exponential to polynomial so that we can have efficient multi-party distributed point functions for any polynomial number of parties. And as our main result, we show that the answer is yes. And we give a construction of multi-party distributed point function where the share size is n cubed times square root of the domain size. Okay, so for the rest of the talk, let me give you a very high-level overview of how we combine this construction. And in order to know how we construct our construction, it is instructive to look at how BGI-15 give their construction. And it's even instructive to start with the two-party case. So remember, we're trying to get a function secret sharing for the point function, where the truth table is something that is almost zero everywhere except for one special location. So the first thing you do in the BGI-15 template is that you divide this size d vector into root d many chunks of size root d. And to share this truth table to two parties, what you do is essentially you sample a PRG seed per chunk for each party. For the non-special chunk where things should sum up to 0, you give two parties the same seed. For the special chunk where things should sum up to a non-zero, an indicator vector, you give them different seed. And the way they are going to expand this share to generate additive sharing of the truth table is to expand the PRG. And you can see that for the non-special chunk where things should sum up to 0, we already have correctness because they get the same seed and they will cancel each other. For the special chunk, we get two independently fresh seed, so the PRG expansion will sum up to something pseudo-random. And in order to restore correctness for the special chunks, there's a standard techniques first, which is applied to a correction string, which is essentially the shift you want to apply to this special chunk to make things agree with the indicator vector. And remember that we cannot directly tell party which chunk to apply this correction string that would violate privacy. So the way to do that is that the trick is that you give a control bit indicating which chunk is the special chunk. And this control bit is additively shared among the parties. Okay, so one crucial thing I want to mention here is that this correction string is pseudo-random in the adversary's view, because no matter which party, P1 or P2 will corrupt, there is one seed that is never given to the adversary. So that contribution of that seed will make sure that this correction string is pseudo-random. And finally, the efficiency of this construction is square root of d, because you get square root d many PRG seed, and the correction string is also square root of d. Okay, so this is a simple scheme where in the two-party case where we have efficiency square root of d. Now, the very clever observation that BGI-15 observed is that you can actually extend this template to beyond two parties. And it's actually following roughly the similar idea, except that where the way we distributed the seed is going to be slightly more complicated. And in particular, you're going to give each party more than one seed. For example, here, for each non-special chunk, you're going to sample 3 seeds, the red seed, the blue seed, and the brown seed. And each seed is going to give repeatedly twice to 2 different parties. And if you still expand the PRG seed and sum them up, you will find that for the non-special chunks, they will sum up to 0 because every seed is shared twice. So they will cancel each other. Now, I still haven't told you how do we sample the seed for the special chunk here. And the BGI-15 has this interesting observation that you can sample an additional seed, the black seed here, and give the seed in this distributed seed in this manner. And the point here, the 2 point here is that first, if you look at the special chunk, the expansion of the PRG and sum up, the sum is still pseudo-random. So no matter which 2 out of these 3 parties you corrupt, there is still a seed that is only given to the honest parties. So that seed will guarantee that this string is pseudo-random. On the other hand, this 2 mode of distributing seed is okay because the 2 mode is actually indistinguishable in the adversary's view. No matter which 2 party you corrupt, you cannot tell the difference between a special chunk and a non-special chunk, because essentially what you see is that you see a seed twice and you see 2 different seeds. Okay, so this is their construction for the 3-party case. So the first thing we do in this work is to take their construction and introduce an abstraction that we call special combinatorial design. So this essentially what we do is that we visualize this seed distribution process as a bipartite graph. In this bipartite graph, the left vertices are all the parties, and the right vertices are all the seeds. And the edge in this bipartite graph defines how you are going to distribute the seed to different parties. And there are 2 different bipartite graphs because you need a way to distribute the seed for the non-special chunks and the way to distribute the seed for the special chunks. And in order for this different mode of distributing the seed to work for the BGI template, we need these 2 bipartite graphs to satisfy 3 properties. First, the correctness property saying that G0, which is how you distributed the seed for the non-special chunk, this should sum up to 0. Which means that the degree of all the right vertices, which is the seed, needs to be distributed even number of times. And for the special way of distributing these seeds, we need this correction string to be pseudo-random. meaning that no matter which subset of parties you corrupt, there needs to be a seed that guarantees pseudo-randomness that is only seen by this honest party. So per party, there should be a seed that is only connected with this party. And finally, for privacy, to that this two mode of distributing seeds should be indistinguishable from each other. That's the privacy guarantee. And given this special abstraction of special combinatorial design, you can directly, it's not hard to show that you can directly plug this into the BGI template and get a multi-party distributed point function, as long as this special combinatorial design satisfies all the three properties that I just mentioned. And at this point, I want to highlight that the efficiency of this special combinatorial design is very important because the size of the special combinatorial design will define the size of the DPS shares. And as I mentioned, BGI 15 can give you, for any number of parties, you can give a multi-party distributed point function construction. You can view the BGI 15 construction through the lens of our special combinatorial design. Essentially, what they do is that they give a deterministic construction of this special combinatorial design such that the number of vertices for n parties is 2 to the n. And by deterministic design, I mean that these two biplot graphs are fixed biplot graphs. And our first result is a lower bound showing that if you are insisting on a deterministic construction of this special combinatorial design, the size of this graph has to grow exponentially in the number of parties. And in that sense, the BGI 15 construction is optimal. So I won't go into this lower bound result and refer you to the paper for it. Now, in order to bypass this lower bound, that strong lower bound that showing that the construction has to grow exponentially in the number of parties, the natural idea is that we're going into randomized constructions. So by randomized construction, I mean that these two biplot graphs are no longer fixed, but they are a distribution of biplot graphs. And once we go to randomized construction, our idea is quite natural, that basically for G0, what we sample is just a random graph with degree 2. So we will sample L to be determined, many of C's, that we will distribute each seed twice. So the degree of these seeds are 2. This is the blue part is basically the G0 biplot graph. And for G1, we will additionally sample some other seeds that will only given to one party. So these seeds, the green part, will have degree 1. Now, in order for this to check that this is a valid randomized combinatorial design, we need to check that the three properties that we insist are satisfied. First, the correctness will hold because correctness means that G0 should only have even degrees. And this just holds by design because we sample each seed with 2 neighbors. The second thing is that for pseudo-randomness, we need in the G1, which is the blue part and the green part, that each party should have a dedicated seed. And it's not hard to see that if we sample enough seeds, the T here, to be large enough, in particular order of n, then with high probability, each party will have a dedicated seed. So pseudo-randomness is also relatively easy to show. Now, the final thing is that what about the privacy? Why these two graphs indistinguishable from each other? And in fact, you might think that they're quite distinguishable because one graph is a subgraph of the other one. Well, the point here is that if you think about the adversary's view, an adversary corrupts a subset of parties, what does the adversary see? The adversary sees basically a bunch of seeds, some being sampled, some it receives 2 times, some it receives single times. And the first observation is that the only thing that matters is how many times you see a seed sampled twice, and how many times you see a seed sampled once. So I denote these two counting by S and T, S for single, T for twice. And the reason is that condition on how many seeds you see twice, how many seeds you see once, the actual configuration of how this seed was distributed among the corrupted parties is just purely random. This is the same for both G0 and G1. So in order to argue the statistical closeness, you just need to look at these two counting numbers. Okay. Now the second observation is that the distribution of T, which how many seeds you see twice, is identically distributed for both G0 and G1. This is because what seed you can see twice? Only the blue part. And the blue part is identical for G0 and G1. So you will the distribution of the number of seed you see twice is identical for G0 and G1. So now the final thing is that condition on how many seed you see twice, why is the number of seed you see a single times is indistinguishable between G0 and G1. This gets technical, but I will just give you a one-line summary. It's because the number of seed you see once in G0 is basically a summation of many Bernoulli distributions. So it behaves somewhat like the blue curve in the front here. And the number of seed you see once for the G1, which is the green curve here, is basically the blue curve shifted by this additional seed that we sampled, which the shifted amount is roughly order of n. And in order to mask this, to make sure that these two distributions are statistically close, you basically informally just need the standard deviation of this blue curve to be larger than the shifted amount. And without telling you any technical details, basically we show that if L, the number of seed we sampled with degree 2, are n to the 4th power, then you can guarantee that these two graphs are statistically close. Okay, that basically concludes our construction for the randomized design. So let me sum up our construction in the bigger picture. So basically we take the BGI template and abstract this special combinatorial design abstraction and give a special randomized special combinatorial design where the size is order of n to the 4th total size. So per party, the share size is going to be n cubed. And you repeated this root d many times, so that's why the DPF share size is n cubed times root d. And one thing that I've been sweeping under the rug is that this two graph can only be inverse polynomially close. And in order to get negligibly closeness, we invoke this very nice result by Boyle et al. That you can generically amplify any weakly secure DPF to be strongly secure DPF. That's how we handle it, and I leave it at that. And with that, I will end my talk here, and happy to take any questions.
Yes, Shai?
When you use it for secure computation, where does the randomness for the randomized design come from?
Yeah, so when the seed is sampled by the trusted party, so this trusted party is going to sample some random seed and flip some coin to decide which party to give to, and you can use a DKG to emulate that.
Okay, yes.
Yeah, thanks. Great talks. I'm wondering how likely do you think are we going? Like, is it possible, or do you think it might be like decreasing the key size from like square root to like polylog? Or...
Yeah, I think that. Oh no. In Minicrypt, I suspect not. Other than that, I have no idea.
Okay, thank you.
Yeah.
Okay. So let's thank Mingguan again. Okay, the next talk is on computationally differentially private inner product protocols, imply oblivious transfer by Iftach Heitner, Noah Mazor, Jad Silbak, Eliad Sfadia, and Chao Yan, and Chao will give the talk.
Thanks. Hello, everyone. This is with Iftach Heitner, Noah Mazor, Jad Silbak, and Eliad Sfadia. So the motivation of differential privacy is that when we do an analysis on a database, it is possible to leak the privacy information by the output. So consider two database X and X prime that they have a different entry. We can compare the output and distinguish these two outputs and know the second entry is from which database. So even if we have a secure way to compute it, we cannot preserve a very good privacy. To solve this problem, differential privacy requires that if we change one record, the output distribution should not change too much. So even in the worst case, if we have an adversary that know all other records, he cannot know too much on the remaining one. And we say a mechanism is epsilon delta dp if for any neighboring databases x and x prime, the output distribution is epsilon delta indistinguishable for any distinguisher. So let's see an easy example. Say now Google wants to output the number of users with high blood pressure. It can first count this number and then add a noise on it. A fundamental mechanism called Laplace mechanism samples noise from the Laplace distribution, and it can make it private. The property of Laplace distribution guarantees that with high probability, the noise is upbounded by a constant. So we can privately compute the sum with a high accuracy. And we say it is centralized DP if the mechanism M can access the entire database X. And in this paper, we consider a distributed setting. In the two-party DP setting, we have two servers, A and B. A has database X, B has database Y. These two servers use a protocol to estimate a function f on X and Y. The goal is to estimate f while preserving epsilon delta dp. And we assume A and B don't trust each other. So for party A, it requires that for any X and any neighboring Y and Y prime, the view of A is epsilon delta indistinguishable. And here the view can include import coins and transcript. And we also have the same requirement for B. Let's consider the summation task again. Say now Google and Apple wants to compute the total number of users with high blood pressure. But Google doesn't want Apple to know the information of its users. So in this case, the two companies can first independently add noise on their sums and then combine them. And in this case, the total noise is the sum of two constants, and we can know that computing the sum can be very accurately in the two-party DP. Inner product is another useful task. It is used to measure the correlation between two databases. But this is more challengeable than computing the sum because we cannot easily add noise on two vectors and then combine them. So let's see what we know on DP inner product. In generalized model, it can achieve constant error just by the Laplace mechanism. And in two-party setting, consider one easier case that two vectors are uniform imports. And then we can easily output 0. And with high probability, the noise is bounded by root n. And it can be generalized for every import distribution by a technique called randomized response. But unfortunately, we cannot do better. A lower bound work shows that for every DP protocol, the noise must be root n. That's bad. But if we relax the requirement to be computational two-party DP, we can achieve constant error again using cryptography. Here, the cryptography is oblivious transfer and secure MPC. So what is computational DP? Recall that in standard DP, we require that the output distribution is indistinguishable for any unbounded distinguisher. But actually, we don't need such a strong requirement. We can only require it indistinguishable for efficient distinguisher, and we call it CDP. And we can also move this requirement to a two-party setting. In two-party CDP, we only assume the adversary is computational efficient, And now we only want to preserve epsilon delta CDP in two-party setting. The good thing is we can get CDP via secure multi-party computation. If we have a centralized DP mechanism M, we can use MPC to simulate it. So if this M is centralized epsilon delta DP, then the corresponding protocol pi is epsilon delta CDP. And we can get secure MPC via oblivious transfer. And for inner product, the Laplace mechanism can easily to compute it. So we have an accurate inner product protocol in two-party CDP. Okay, so now we know that we have a good method to use OT to get very accurate CDP protocols. So the question is, do we have to use OT? Is that possible to have a smart method to get accurate CDP without using the OT assumption? This is a complexity hierarchy. It has 3 levels. On the bottom, there's one-way function, key agreement in the middle, and the oblivious transfer is on top level. We say a task is non-trivial if it is possible in two-party CDP, but impossible in two-party DP. And we are interested, where is the non-trivial two-party CDP? By previous discussion, we know oblivious transfer implies it. And we also know non-trivial two-party CDP can imply a one-way function by an easier construction. For concrete task, we know CDP XOR is equivalent to oblivious transfer. But this is limited because XOR is an easier task that only over 2 bits. So we are more interested in natural task. IP is such a candidate. In one previous work, they showed that one-way function cannot imply non-trivial CDP IP. And one important work by other authors in this paper, they show that CDP IP implies key agreement. So that means key agreement assumption is necessary in this task. And in this work, we show CDP IP is equivalent to oblivious transfer. So unfortunately, OT assumption is necessary to construct such a protocol. This is our main result. Mildly accurate epsilon delta CDP for inner product implies OT. Here, epsilon delta are reasonable parameters. Epsilon is a small constant. Delta is 1/n. Mildly accurate means with high probability, the error is bounded by N216. Notice that it's weaker than the information theoretical barrier √n, but that's enough for our target. And our work shows that mildly accurate implies very accurate, because if we have OT, then we have MPC, and then we can simulate centralized DP mechanism and get constant error. Okay, let's see the proof overview. Our target is to construct OT, in which Alice wants to deliver X to Bob, and with half of chance, Bob receives it, and Alice doesn't know what Bob receives. We use a tool called weak erasure channel, which is introduced by Washlager. In this channel, Alice and Bob wants to use a protocol to exchange information. And in the non-erasure case, they successfully do it. In this case, alt A equals to alt B. In the erasure case, Bob outputs nothing, and he doesn't know what's the value of alt A. And we also want Alice doesn't know if alt B is bought. The Washlager shows that If we have such a magic channel, then we can use it to construct OT. Okay, in our work, we use CDP/IP protocol to construct an approximate version of weak erasure channel. So in our protocol, at first, Alice and Bob randomly sampled inputs X and Y. Then they use a magic CDP/IP protocol to compute the inner product of X and Y. Then Alice randomly select one set of indexes R and send XR to Bob. In the non-erasure case, Bob compute out minus XR, out minus the inner product of XR, YR, and deliver Y minus R to Alice. Here, Y minus R is the remaining vector in Y. And Alice compute the inner product of X minus R, Y minus R. In the erasure case, Bob outputs nothing. But he will select another index of another set of index and add random noise on them and deliver the noisy Y minus R to Alice. For Alice, that's the same. And we claim that in this channel, Alice doesn't know if out B is bought. And if out B is bought, Bob doesn't know the value of out A. And this weaker version of weak erasure channel, we can amplify it to standard WEC, then we can get OT. To see the agreement, notice that we assume we have a magic protocol that have a high accuracy in inner product task. So it implies that out A is approximate to out B. For the secrecy of Alice, the proof follows previous work, HMST. They show that for any PPT if, he cannot compute something that is close to out A by the transcript. And it implies if out B is bought, Bob doesn't know what's the value of out A. For the secrecy of Bob, consider a toy case that Bob only add noise to 1 bit. The key observation is that given DP mechanism M and a database X that has high minimum entropy, consider another vector Xi that randomly flip 1 bit on X. Then for a random R, if there's any adversary that can distinguish XR and XIR with a good probability, then it can be used to contradict the DP requirement of M. And this is a constructive proof, so it also works for CDP. Okay, then in toy case, we only flip 1 bit, and it can be extended to K random indexes, which is used in the erasure case in our protocol. So we can conclude Alice doesn't know if out B is bought. So in conclusion, we show that mildly accurate CDP/IP implies OT. The open question is, we don't know the answer for error in the range N216 and root N. And we are also interested in more functions. It can help us understand the complexity of computational differential privacy. Okay, thank you.
Okay, thanks. Any questions?
Are there any questions about the relationship between these two primitives in terms of round complexity?
We don't consider the round complexity. We only assume there's a perfect MPC that can simulate everything. Yeah, we don't consider it.
Okay, thanks.
Any other questions? Maybe one question of my own. So the current strategy is very different from the previous implication of key agreement, in the sense that in the key agreement, it was a more general theorem that anything non-trivial implies key agreement. Any hope to extend the previous more general approach to show that it actually implies oblivious transfer?
So the main difference in this work is that we use the weak erasure channel to construct OT. And since this is a constructive proof, we lose some polynomial degree in this process. Yeah, I don't see how to make it. Yes.
Okay. If there are no further questions, let's thank Chao again. Okay. Yes, we're slightly ahead of schedule, but we'll continue. So the next talk is on additive randomized encodings from public key encryption by Nir Bitansky, Saroja Arabeli, and Rachit Garg. And Saroja will give the talk.
Hi, I'm Saroja, and today I'm going to talk to you about additive randomizing encodings. This is joint work with Nir Bitansky and Rachit Garg. Okay. Okay. So we're going to start with a really simple question where I'm up here giving a talk, and you are the very enthusiastic audience, and I want to know whether or not you like my talk. But we would rather not do this with a public show of hands because I'm really petty and I'm going to be really mad if you say you don't like my talk. So this gives us a pretty natural scenario for MPC where I'm tallying up all your votes and you don't want me to learn anything other than the function output. So there's many MPC protocols to do this that require multiple rounds of interaction. But I don't want to do that. You all don't want to do that. We don't want to sit here all night coordinating all these rounds. And if you've been to any other MPC talk, you know that we do not like rounds. So a pretty obvious question to ask is, can we do this vote in one round? So here, I'm going to be a little evil and try to find out the third person's vote. So what I'm going to do is change Alice's vote to yes, Bob's vote to no, and then whatever the outcome of the vote is allows me to learn Charlie's vote. So this is impossible unless we have a setup involved. But I really want to do this vote in one round, and I really don't want to have a setup process involved. So I'm going to add a little additional constraint where we have this box at the front of the room, and you all can drop slips of paper into the box, and I can only see the votes after it's all been shuffled. So this is like an anonymous box, and this green shuffle acts as a randomized shuffle. So now the question is, can we do this vote? So let's say, for example, the votes are yes, yes, and no, and I don't know who voted in what way. I'm still going to try to learn as much as I can about the vote. So I'm going to change one of the votes. And let's say I change it to no. So this is going to change the outcome of the vote. So I still learned that the vote was close in this case. So unfortunately, it's still impossible. So one final modification I'm going to make is I allow Alice, Bob, and Charlie to put multiple votes into the box. So here we call this the multi-message shuffle model. This has been a pretty popular model recently in differential privacy as a relaxation of central privacy, which gives better utility and privacy trade-offs. So now when I try to learn or change some of the votes like I did before, I think about how to do this and I have no idea. Like if I change some of the votes, I don't know which messages correspond to Alice or which messages correspond to Bob. So the same attack from before no longer applies. Okay, so the main question we explore in our work is under what assumptions does MPC in the shuffle model exist without setup? Okay, so you can take a second to think about what your guess might be for what assumptions you can construct it from. From IO, it seems pretty likely because you can construct most things with IO. It would be really nice to get it from LWE since it's post-quantum. You'd think it would require at least OT because a lot of MPC protocols require OT. But in our work, we were very surprised to discover we could construct it generically from public key encryption. And the way we do this is by constructing something called additive randomized encodings, which were introduced by Yuval Ishai and Eyal Kushlevitz, Tal Rabin. So in additive randomized encoding, we have n parties. They locally encode their function, and we have a trusted addition. So then the addition of the encodings are sent to an untrusted evaluator who is only allowed to learn the function output. And this falls under the general paradigm of randomized encodings. So to be a bit more specific about our security requirement, we want there needs to exist a PPT simulator that can simulate the sum of the encodings given only the function output. And I do want to emphasize, we are assuming here that the evaluator does not collude with any of the parties. And you can also define a stronger notion of robust ARE, which does require security against insiders, but this will not be the focus of today's talk. Okay, so why are we looking at ARE to construct shuffle MPC? This is because the trusted addition assumed by ARE can be implemented in the shuffle model. And this was a paper by Yuval, Kushlevitz, Ostrovsky, and Sahai. And the corollary described in HIKR is that if we can construct ARE for a function f, then that gives us non-interactive MPC without setup for that function f in the shuffle model. Okay, so that reduces our question from before of under what assumptions does shuffle MPC exist to under what assumptions do additive randomized encodings exist. So previously in HIKR, they constructed ARE for all functions f under the decision squaring XDH assumption, which is based on pairings. So our main result is getting the more general assumption of public key encryption and constructing additive randomized encodings from this. Our paper also has a more efficient construction from CDH, but we will not be talking about that today. Okay, so let's get into the construction from PKE. So our main idea behind this construction is this notion we define called one-sided ARE for two parties. So this is a weaker notion of ARE where given the sum of the two parties' encodings, we're also allowed to leak the first party's input. So here the simulator can also have access to the first party's input. Okay, so it turns out one-sided ARE is very straightforward to construct for any function f using techniques from HIKR. So the main question that we sought out to answer is, can we lift one-sided ARE for any function f to full-fledged two-party ARE for any function f. So today I'm going to talk about how we do this lifting step using public key encryption. Okay, so the first thing we start with is a one-sided ARE, and then we ST ARE at it. Wow, okay, so yeah, you might argue maybe this is not our most important contribution, but let's see what this gets us. Okay, so when I see input X that leaks as a cryptographer, I just want to like shove it under an encryption. So that's exactly what we do. So we encrypt X, and so we want to compute f of xy. So we use an FHE scheme to try to compute the encryption of f of xy. So this is our first attempt, but the problem is we can't decrypt if we do this. So we're starting with this FHE encryption, CT prime, and we also need to output the FHE secret key to decrypt, but then this again leads us back to the same problem where we're now leaking X. So to rephrase the question, so now that we're leaking X, we again shove it under an encryption. So we encrypt the FHE secret key. And now the question is, we want to compute this decryption function of the FHE ciphertext. And here we parameterize the decryption function with CT prime, and the input to the function will be the secret key. So it turns out we already know how to do this using the weakest version of public key functional encryption. And here, what this means is the setup outputs a public key and a master secret key. Using the public key, we can encrypt a message M. Using the master secret key, along with a function description, we can output the function secret key, which allows us to decrypt and get the function output. So here, the security guarantee is that given the public key, the encryption, and the function secret key, this only leaks the function output in addition to the function description. And this is constructible from PKE. Okay, so now we go back to our construction from before using FHE, and we combine it with FE now. So like before, we had the encryption of f of xy. We want to compute this decryption function where the input is the secret key, and this would give us our desired output. So now, given this information, we have this function capital F, and we want to compute this function on the encrypted input. So what we want our ARE to output is the encryption of the FHE secret key, which is the input to our capital F function. And we need the function secret key for this capital F function. Okay, so to use one-sided ARE to get these two things, first we'll output the function secret key. So we start with an encryption of X like before. Party 2 will generate the FE setup and use the master secret key. So here the one-sided ARE will compute CT prime just like before. We'll get the function description F CT prime, and now combining that with the master secret key, we can output the function secret key. Okay. But here we're still missing the encryption of the FHE secret key. So the natural thing to do is we want to plug in the FE public key and the FHE secret key in order to compute this encryption. So what we try to do is just plug it into the inputs of the one-sided ARE. But now this has the same problem as before because party 1's input leaks. So now again, we're leaking the FHE secret key. So the really crucial idea here is that we can compute these two things separately. So we can reverse which party leaks the input So for the second one-sided ARE, we output the encryption, and now Bob is the party who leaks his input, which is the FE public key. And now the FHE secret key, which Alice has, remains secret. And we use the same one-sided ARE from before to output the function secret key. So this is a construction that works, and it's but FHE is a bit of a strong assumption, and we're not really using all of the security guarantees by FHE. If we look a little bit closer about what FHE is actually giving us in this construction, it's giving us security in the first one-sided ARE, and we notice that the only things that leak in the first one-sided ARE are Alice's input CT, and the function secret key leaks the function description. So that leaks CT prime. So this is really where the FHE security is used. FHE is guaranteeing that CT and CT prime together do not leak anything. So if we take a closer look at what the security guarantee we want is that we have Alice who has an input X. She sends an encryption of X to Bob. Bob now sends back the encryption of f of xy. And what we need here is just security against an external observer. And we're not really using at all the compactness properties of FHE. So we can actually have a much simpler implementation of this functionality, where instead of FHE, Alice can just send over a public key, and now Bob can send back an encryption of y, and then Alice can decrypt with her secret key and compute f of xy. So now this gives us our final ARE, where we replace the encryption of X with Alice's public key. We replace the computation of CT prime with the computation of encrypting Y, and then we replace the capital F function. Before we were decrypting the FHE encryption, but now we're decrypting the public key encryption and computing f of xy. So that concludes our construction. So I do want to say that when we first started working on this problem, our goal was to construct ARE from some post-quantum assumption. So we were very surprised to find that we could do it generically from public key encryption. And we were even more surprised to learn that we can actually just compute or construct ARE information theoretically, which is a recent result we posted. And we can do this with negligible correctness and security errors. And the techniques follow a very similar leaky ARE paradigm, where we have a leaky version and we lift it to the full-fledged ARE. But I will say the PKE construction still has one advantage, which is that it has perfect correctness. So this leads me to remaining open questions. So the first one is that, does every function have a perfectly correct statistically secure ARE? Because our recent result, BEGI, does not have perfect correctness. And there are still remaining questions in the robust ARE setting, which I didn't really talk about today. So here we require security against insiders. And what's known from HIKR is that efficient, robust ARE implies obfuscation. And Bitansky and Freze also have a construction of robust ARE for all functions from IO, and assuming either LWE or DDH. But if we look at a little bit simpler class of functions, particularly functions with a finite domain, we want to know whether we can construct robust ARE from assumptions weaker than IO. Thank you.
Okay, thanks, Roger. Any questions?
I think your construction makes non-black box use of public key encryption. Would you bet money on the possibility or the impossibility of the construction from black box PKE?
I think if I were to bet, I would say there's maybe a separation, but for black box construction. But yeah, we do have a statistically secure construction. So no, yeah, sorry. Actually, no, we have a statistically secure construction. So yeah.
I meant for a perfect correctness case, for the perfect correctness.
Yeah, perfect correctness. Okay, yeah, I guess, yeah, maybe it could go either way, but I would probably start out by trying to prove a black box separation. Yeah.
Okay, any more questions? Okay, thanks, Saroja. Okay, the last talk of the session is a remote talk. Is the recording available? Great, so the last talk is on efficient pseudo-random correlation generators over Z over P to the K by Ze, Li, Xiaoping, Xing, Yizu, Yao, Chen Yuan, and Ze will give the recorded talk.
Present our work, efficient pseudo-random correlation generators over ZPK. My talk consists of 3 parts. The first is on the motivations, and second is on the results, and the last on our techniques. MPC considers honest parties and dishonest parties. Modern MPC considers a preprocessing model. In the preprocessing phase, the parties generate some correlations. During the online phase, the correlations are consumed. The problem is how to efficiently produce many correlations. For MPC over Z2K, why we consider MPC over Z2K? There are many reasons, like the modular operation is free in modern computer architectures, and it's more compatible with binary operations. It's easier to compare existing programs to MPC program. There are some problems to achieve MPC over Z2K, like the non-invertible elements, and the non-invertible elements can also sometimes are also the zero divisors. There exist some works for MPC over Z2K. There are 2 main methods. First one, extend Z2K to a larger range. The second use it's still extended to a larger range, but it's a special extension. It's the Galois extension. How to produce OT or OLE correlations? For the field case, there are 3 methods. The first one is based on the OT or OLE approach. The second one is based on homomorphic encryption. The third one is based on the PCG. For ring case, only the first 2 methods have been explored. However, the OT-based approach has a quantitative blow-up in the ring size, and the homomorphic encryption approach has high computational cost and at least linear communication cost. Next, we recall the PCG definitions. For target correlation R0, R1, the parties generate small seeds K0 and K1. And the small seeds can be expanded to long correlations R0, R1. The correctness requires the expanded correlation is computationally indistinguishable from the target correlation. The security says the expanded correlation and the seed is computationally indistinguishable from a simulated seed, simulated distribution. Next, I briefly introduce our results. Assume the RLPN or QASD assumption over Galois ring and function set sharing. We construct a programmable PCG for OLE over any Galois ring with logarithm seed size and quasi-linear computational complexity. Here, this theorem contains result both for ZPK and general Galois ring. Next, we obtain a two-party PCG for speed D2K type authenticated multiplication triples with logarithm size and quasi-linear computational complexity. We can also extend our result to PCG for matrix triples and circuit-dependent processing over Galois rings. Here is a brief theoretical efficiency comparisons between our method and the previous method. We can see the communication cost of our work is on logarithm on n, and the OT-based method has a factor of lambda times capital N, this two. And also the homomorphic encryption-based method also has this lambda times n factor. Here is the concrete efficiency of our results. For k equal to 32, it's about 100,000 triples per second. Next, we present our techniques. We first record the PCG construction for FQ OLEs. The idea is to reduce multiple OLEs over FQ to one OLE over a polynomial ring. The polynomial ring is defined in this form. In fact, the polynomial ring is isomorphic to FQ power n. Assume the RLPN assumption and the QASD assumption over this polynomial ring and function sharing schemes. We can obtain a PCG construction. A is public and S sigma, E sigma are random T-sparse elements. And then we can compute B sigma, and it's pseudo-random. B0 times B1 contains some cross terms S0 times S1, S0 E1, S1 E0, E0 E1. The cross terms are sparse, so they can be succinctly shared via functions to sharing. Generally for domain size n, the functions to sharing has size logarithm on n. However, this method only works for q greater than n. Actually, it's from this definition and the isomorphism. For smaller q, they considered the multivariate polynomial ring. And this method only works for q at least 3. To construct a PCG over any field, recently LXYY defined a function for the polynomial ring elements. The trace function is defined as sum of p power n. And they also proved the trace function and the isomorphism are available. So they obtained this result. Now we briefly summarize the requirements of previous PCG constructions. First, they require an isomorphism between the polynomial ring and the target, the vector of the target ring or field. And also a trace function for the polynomial. And also the trace function is required to satisfy some properties. Next, we recall the Galois ring, some preliminaries of the Galois ring. Given a degree m polynomial Gx, such that Gx mod p is a irreducible polynomial over Fp, the Galois ring of degree m is defined as Zpkx mod Gx. Let zeta be a root of Gx. Then any element A of the Galois ring can be defined as this form, or it has a unique representation in this form with respect to the zeta here. Next, we recall the Frobenius map and the trace function definition. The Frobenius map is defined as x to the power p to each zeta. You can see this one. For here, keeps the ai, and each zeta power I is zeta p times power I. Then the trace function is defined as sum of Frobenius map. Additionally, the trace function map a Galois ring element to a ZPK element. We first show the ring LPN and the QASD assumption holds over Galois rings. For the univariate ring and the multivariate ring, the ring LPN assumption says for uniform AI and each EI is a random T-sparse elements of R. Then this inner product is computationally indistinguishable from the uniform distribution. There exists a security reduction from ring LPN over the Galois ring to the ring LPN assumption over finite fields. Directly mode P. After mode P, the instance of ring LPN over Galois ring becomes an instance of ring LPN over finite fields, and the error weight is slightly changed. Next, we establish isomorphism between the polynomial ring and the vector over Galois ring. Let G bar x be a primitive polynomial and Gx is a Hensel leaf of G bar x. Then the Galois ring is defined as Zpkx modulo Gx. And zeta is an element of this Galois ring of order Pm minus 1. Let the polynomial ring be in this form with this capital N divides the order of the zeta. Then x power n equal to 1 has n root alpha 1 to alpha n. Each alpha I are power is a power of zeta. With the alpha I defined in the above form, there exists an isomorphism between this polynomial ring and GRN. For any element f, it can be viewed as the evaluation of f at alpha 1, alpha 2 to alpha n. In Galois ring definition, the G bar x is required to be irreducible. Here, we require it to be stronger, the primitive. With this isomorphism and the ring LPN assumption, we obtain the first PCG construction for Galois rings. Like in this form, we obtain B0 times B1, and then we apply the isomorphism for each B0, B1, and W1. And this result, this equation has only 4 sparse terms. Each has weight T squared. To construct PCG for ZPK, we recall the definition for the definition of trace function for polynomial ring over finite fields. The trace function is defined as sum of f power to pi. How to extend this definition to polynomial ring over Galois rings? If we directly use this definition, I mean for Galois ring, the sparsity does not. Actually, the sparsity holds for field because the characteristic of the finite field is P, but for Galois ring, it's P power to K. The trace function for the polynomial ring can also be viewed as sum of some Frobenius maps. And the Frobenius map for Fj, I mean the finite field elements, there exists a standard definition. For the intermediate x, it's defined as x power to pi. If we consider this definition for Galois ring, the Frobenius map is well defined. The problem is how to define this one. Actually, we use the same definition as the field case because we consider the trace function. We consider the trace function and the isomorphism are abelian. I mean, we make some operations between these two maps. So for any f, the Frobenius map can be defined as sum of products of the Frobenius map. With given this Frobenius map, we proved it satisfies some desired properties like the additive homomorphism, sparsity preserving, and also after m times of the Frobenius map, then f becomes itself. In particular, they proved this Frobenius map and the isomorphism are abelian. With the Frobenius map, the trace function can be defined as the sum of the Frobenius maps. And also, the trace function and the isomorphism are abelian. And then we can obtain this result because they are abelian. And also, we can prove the trace function satisfies some desired properties. With this trace function, we can construct a PCG for ZPK OLE. For each B0, B1, W0, W1 here, we apply the trace function. After the trace function, we then apply the isomorphism. To obtain the product of the trace function, we apply this equation. We put the B0 inside the trace function. So the task is only to share B0 times trace B1. In this one, it has only 4m sparse terms, and each has weight t squared. With this trace function, we can also construct a PCG for speed Z2K type multiplication triples. Let delta be the global K. The target is to share delta times trace B0 times B1. And we can also put the delta B0 inside the trace function. Now the task becomes to share delta times B0 times trace B1. And then we expand the product here. We obtain this form. So it has 4m sparse terms. Each has sparsity t squared. 4m sparse terms here. In summary, we constructed a programmable PCGs for multiplication triples over any Galois ring, and also two-party PCG for speed Z2K type authenticated multiplication triple. The remaining problem is how to construct a PCG for multi-party authenticated multiplication triples. Thank you. That's all of my talk.